is explicit, right? And this is Hoyne's method for integration. Hoyne. Right. In fact, actually, it's cubic. If you, I was a little bit sloppy about my math here, but if you go back and check, see that in fact you preserve the cube. So, what's the advantage now? Well, so the only second order method that we had so far was this implicit trapezoid thing, which was not only implicit but had weird properties. Now I have another one that is explicit and second order accurate. Now, this is good, this is useful, and people use this in practice. But what do we have to be careful about? Remember, we're going to go back to our, today we have like kind of a mantra, right? We have these two things we have to check on, that our method has to be stable and accurate. We just improved the accuracy, but we haven't checked the stability of this method. Do you see that? In particular, I just made some weird substitution here, and I haven't shown you that this weird substitution is going to make it explode on the model equation. No? So, let's do that. You see, is this arithmetic getting boring yet? Because it's basically the same pattern over and over again. Yeah. I think this is the last time we're going to do it. Oops. Okay. So in particular, let's start plugging things in. Yk plus 1 is yk. By the way, guess what you're going to do on homework 8, if I remember right? Yeah, so what is f of yk? Well, he's just a yk. And now I'm going to have f of yk plus 1, which we're approximating with this guy, right? So every time we see an f, we can just replace that with an a. Yeah? So the end, you're going to get plus a yk plus h a yk. Did I do that right? I can check if I did it right here. Yk is h of 2, a yk plus a yk. Yes, we're good. Okay, and in particular, when you when the smoke clears and you simplify all of this stuff, right, you can see that now we only have yks on the right-hand side. That's what's making this thing an explicit integrator. Yeah? Then when we simplify, we get that this is 1 plus ha plus 1 half h squared a times yk. What happened? We got yet another random constant number sitting in front of the previous iterate when we plugged in the model. But we kind of expect this to happen for almost any ODE integrator, right? Because if it didn't, then somehow it would be a little weird because we know that there should be some kind of exponential growth. I say that, and then in about half a slide I'm going to contradict itself. Okay, so if you plug this thing into Wolfram alpha, which is what I did, then what comes out is that your h has to be bounded above by this weird square root. Now, what's important here isn't really this formula. In fact, usually what you do is you kind of bound this thing instead of trying to solve this inequality in any sort of tight way. But one thing you should keep in mind is that you should try and compare this with forward Euler. Okay? And in particular, forward Euler looked like something like the inverse of a, 1 over a. 2 over a, in fact. This thing kind of looks like 1 over the square root of a. Right? This is not a good thing necessarily, right? This has very, so in fact, the Hoyne's method is even more difficult to make stable. But what did you get for that? Well, what you earned was that, that this method is more accurate, right? So you have to take a smaller time step for stability, but in exchange for what you paid for that, you got a higher degree of accuracy. Yes?
Is there a problem if a is greater than -4?
Yes, it's unstable.
Okay.
Is that true? Do I believe that? Wait. If a, so this gets really. No, wait. You're good. Okay, so mod a is a positive number. Oh. Yeah, I'm not sure. I'll double check. Yeah, it's a good question. Maybe I shouldn't check. Maybe I shouldn't have trusted my Wolfram alpha. Yeah. Yes.
Did you lose an ace? Like, I'm looking at the arithmetic in the line. I feel like I see the a squared there. A times h a
yes. There should be an a squared here, and that's probably why that inequality is wrong.
Yeah.
Okay. there we are. Life is good. All right, yet another silly mistake made by your instructor. And if you remind me, I will update the course notes and the slides accordingly. Sorry about that. See, it's easy for me to get around too, which is like not promising to you guys at all, I realize, but that's okay. Anyway, thankfully, the beginning of this slide, before we realized I made a mistake, what I was trying to say was it doesn't matter what this analysis is. What really matters is bounding how the behavior works. And what you should know is that Hoyne's method is conditionally stable, meaning that if you take a large enough time step, you will screw stuff up. And in fact, the stability for this method is fairly tight, but what you get in exchange is higher accuracy. Sorry about that. Gosh, it's not one mistake. Incidentally, the course notes for this class got accepted for publication for a textbook, so if you find typos, you should let me know, because I'll fix them and they might actually appear somewhere. Okay, so anyway, at a higher level, right, these methods basically, modulo stupid mistakes that your instructor makes, the basic idea of these methods is that you apply some quadrature method to this integral, and then you use some sort of forward integration scheme that's less accurate, but at the very least is easy to evaluate to get the things as forward time steps that you don't know yet. Yeah. And somehow that's okay, because those guys have h's in them. And so the Runge-Kutta class of integrators basically does this for different higher and higher order integrals here, and in the process gets higher and higher order estimations and time stepping strategies. I think, by the way, the cost of having to take smaller and smaller time steps is kind of the name of the game. Yeah?
So this is, how would we compute f of y of t here? Is it using forward Euler?
Yeah, so remember the trick that we already used, right? Yeah, we just used forward Euler f of y of t, which, by the way, is an indicator that stability for these things could be pretty bad, right? Because we put forward Euler into some other thing, right? So we kind of expect our stability to be limited by that of forward Euler. Cool. Right, and we can use these nice low order integrators to get good students. So the most popular version of this is RK4, and this is without doubt the #1 integrator that you will see in everyday life, and it is fairly accurate and fairly stable. And we will not attempt to derive it in lecture today, because if you think I get this one wrong, then this one's even worse. But basically, you use exactly the same strategy that we already used for the trapezoid rule, but instead of using trapezoid, you use the Simpson's integration strategy. So anyway, obviously I don't expect you to have this formula memorized every time I need to use an integrator at Google for this, load it up and type it in, and it just works, and life is good. But you can kind of see that that similar thing is going on to what we just talked about, right? Because you can see that this guy is basically doing some different steps of forward Euler to get to where you want. In fact, actually, I think RK4 uses kind of a magic trick where it uses forward Euler for the first one and then some kind of funny half midpoint thing for the second one. But the details aren't important here. What's important here is that the class of RK integrators is all about using quadrature, and basically by having higher and higher order quadrature rules, you can get better integrators. Yeah? And thankfully for us, there are people in the CME department who have spent a lot of time working out all these different formulas. Cool. All right. So there's one more class of integrators that I do think is worth mentioning in class before we move on to more interesting stuff. And that's because it contrasts a little bit with what we've already seen. Now, remember that sort of the equation that I keep telling you guys is the one that we really care about for understanding stability locally is just y prime equals ay, right? Just the simple linearized ODE. But the thing is, we know how to solve that ODE, right? Like, who are we kidding? We know that this thing is an exponential. So far my story's been a little incoherent, right? I would say, well, we know it's an exponential, but then we're not going to use that fact. We're going to plug in some random formula and then show that it's worse than what we already knew. Okay, so great. But if we know that it's an exponential, then we might as well use that fact. Yeah? And in particular, even when y is a vector, we know how to solve this. For example, using the eigenvectors of A. Right? So, I forget, on a homework I had you guys derive e to a matrix, right? So in fact, this notation should make sense to you. But even if it doesn't, you can think of this as just encoding the solution that we know how to do from eigenvectors for an ODE, right? It's no more difficult than just the, e to the at for a single line, right? So, Anyway, so we know this, and we might as well apply this fact to make a better integrator. And this makes a class of strategies called exponential integrators. And these apparently are getting a little bit more traction now than they used to. So the idea of an exponential integrator is that you have an ordinary differential equation that you write y prime equals ay plus g of y for some a. Now obviously you can always take f and write it this way, but your strategy is going to be to make this be your first order approximation. And then what we know is that g now, hopefully, if f is nearly linear, then this function g should be very small, right? That is pretty well approximated by its first Taylor series term, right? Well, if that's true, then we should be able to integrate pretty well by just looking at this first term here, just taking e to the at and moving forward a little bit. Okay? So what the class of exponential integrators does is it says, okay, well, we're going to do exactly that. We'll use this a term, and then we're just going to correct a little bit using g. And we're going to put very simple assumptions on this function g that make it easy to integrate. So for example, the first order exponential integrator simply evaluates g, does a forward Euler step in g, and then there's a little bit of algebra you have to do to make sure that you don't accidentally have two terms that are kind of positively interfering. But in the end, that's all it's doing, right? Is that it's using the exact solution for the linear term plus some stupid forward Euler term for the remainder. Yeah? So anyway, the analysis that shows that this method is better or worse than others is somewhat more complex because it is nonlinear. But in a lot of cases, when your function f is pretty well approximated by something linear, then it's pretty clear that an integrator like this would do a good job. Yeah? Okay. So that's it. No more just integration rules for stepping forward y prime equals f1. That's kind of boring. And I already got it wrong like 3 times. But there are integration rules for solving our favorite equation, which is f equals ma, that are worth noting. Yeah? So remember, we made kind of a funny reduction in our last class, and then we have applied it ever since. Right? Where we said, okay, our favorite equation f equals ma is second order, right? He involves 2 derivatives of position, right? Velocity and acceleration. But in fact, we can think of it as a first order PDE by making this substitution that I wrote explicitly on the slide here, right? Where we're gonna introduce a variable v of t, and then we'll say, well, y of prime is v stands for velocity, obviously. V prime is a, and then a satisfies that equation, right? So rather than just having some equation in y prime, and t, now we've made this substitution so that it's just a first order system, right? Now, in the end, right, if I'm writing code to solve f equals ma, what do I care about? I care about the position as a function of time, right? That's the output of my code. Any of these other variables, like a of t and b of t that I introduce, are dummy variables that are useful for my integrator, not things that my end user cares about, right? So to that end, if I have a bad approximation of v and a, but I somehow manage to use those to make a good approximation of y, that's okay, right? Because the only thing I really care about is y. In fact, then I could go back at my nice y of t and get better approximations of v and a using our nice divided derivatives we had before. Yeah? So somehow, by making this reduction and then applying these first order ODE strategies that we've talked about for a lecture and a half now, we actually kind of hit the fact that we can take advantage of additional structure here that we don't have in other problems. Hopefully this motivation makes some sense. Yeah? So now, and I'm going to talk only about strategies that do up to second order ODE, but the extensions here are pretty obvious. Now we're going to say, okay, we're explicitly going to carry around y, v, and a, and we're going to treat them separately. We're not going to be quite so democratic about it like we were before. Right? In particular, why we think this might make sense is let's look at the Taylor series for expanding y, t plus h. It's sort of a similar motivation to some other strategies we've already talked about. Right? Well, that's y, but then the place where the velocity is going to come into time stepping y forward, look, it has an h in front of it. So if I only know my velocity to second order, right, and then I use that to time step y, well in fact I time step y in a nice third order way because I put an additional h there. And even better for the acceleration because he's got an h squared. Yeah? So we can have really bad approximations of the derivatives of y so long as the actual y value is okay. Right? This is sort of a good theme for the last couple weeks of this class, by the way. The more times you differentiate a function, the worse the worse you expect your accuracy to be. And the more times you integrate a function, the better you expect your accuracy to be. Because somehow integration adds stability, right? It's like averaging stuff out. Okay. Unfortunately, integrators in this class are much harder to derive. But such is life. So, I'm going to attempt to derive a class of integrators that's known as the Newmark methods. These are very common, especially in mechanical engineering. And you guys should stop me the second that you think you spot an arithmetic mistake, because there probably will be several. So I'm going to preemptively erase 3 boards here, which should make you nervous. And then we'll get started. Okay. And I also worked these out in the course notes. So you'll notice that your textbook skips to the last step, which is totally cheating. This is humongously non-trivial. And in fact, it's very difficult to find a computer science textbook that bothers going through this calculation. You have to like dig through the engineering library and find an old mechanical engineering book. Anyway, right. So luckily the first formula I have on the board is a good starting point because it's abundantly obvious. Right? And all I'm saying is that you can get the next velocity by starting at the previous one and integrating acceleration. Right? Hopefully this is clear because acceleration is the first derivative of velocity, right? Derivatives and integrals cancel, so this formula is clear. Okay. The next formula you may or may not have already seen. I actually had it before I tried to derive one of these methods, but then I looked back and decided it actually wasn't so bad. So, how many of us have seen this second guy? Does this look familiar at all? Yeah, it didn't look familiar to me. So let's motivate what this is doing. So the idea here, this actually relates to one particular proof of the Taylor theorem. The Taylor theorem says that Taylor series converge to functions in the analytic case. And you see what we've done here is we're going to just keep integrating by parts and pushing off to higher order terms. And in particular, this is what comes out if you iterate this process twice. So let's try and derive this. So we have yk plus 1, right? So v equal to yk plus integral from tk to tk plus 1 of v of t dt. Okay? This much is clear. This is the same as our previous one. Now, I'm going to do something kind of tricky. In fact, your problem set does something kind of similar to this, by the way. Where I'm going to integrate this thing by parts. Now, he doesn't look like he should be integrable by parts, right? Usually you think of integrating a product this way. But in fact, this thing is the product of 1 times v of t. Yeah? And so if I integrate this by parts, what's the cool thing that's going to happen is I'm going to put my unknown function is going to get a higher derivative, and I'm going to get an easy function back out as the thing that I'm integrating. Right? So in particular, let's see here, we're going to get yk, again, it's going to get annoying to carry around. And then if we integrate 1, we get t, and if we differentiate v, we get a. Right? Remember how integration by parts works? You integrate one term of the product, you differentiate the other, and you leave the boundary conditions the same. So this is tk plus 1 minus the integral from tk plus 1 of what? Oh, oops, I'm sorry. That should be a v of t. And here we'll get a of t. Okay, you take the higher order of t. No. See, I'm likely to make a lot of mistakes. But hopefully you guys all agree with me that this is just integration by parts. You can see I integrated the 1 to get the t, right? And then I differentiated the v to get the a. Yeah? Okay, cool. So now let's expand this guy. So now we're going to have, this is yk plus tk plus 1 times vk plus 1 minus tk vk minus integral. I'm tempted to not keep writing the bounds of this integral, but I'm assuming if I do that, we're going to start making mistakes. Oh. Alright, I haven't done anything too exciting yet. But now I'm going to. Because look, here's the thing. So remember that tk plus 1, what do we do to get this guy from tk? We just add h, right? So I'm going to do kind of a tricky substitution here. At least this is the way that I can think about proving this little formula here. Which is I'm going to make him into tk plus 1, right? And then I'm going to make this into the integral of a. Right? And the way that I'm going to do that is I'm going to add and subtract the same thing. Which is I'm going to say that this is y, sorry I'm left-handed, plus hvk, right? So I'm going to insert this new term here, and we'll leave this guy alone, tk plus 1, vk plus 1. But now I added him, so I have to subtract him again, right? Particularly I have to do minus hvk, but look, then we already have a minus tk vk. So if we put all those together, you get a minus tk plus 1 vk, minus the integral from tk to tk plus 1 ta t dt. Okay, so you see all I did was add and subtract this number here, but when I subtracted it, I went ahead and absorbed him into the t. Yeah, so this tk became that tk. Well now I can factor a tk plus 1 out of these two guys, right? So in continuing our long chain of bookkeeping here, which I sincerely apologize for on behalf of whoever this guy is, Newmark. We have that plus hvk minus tk plus 1, and now, in fact, we'll make that plus. But look, so what's going to come out? Well, I have tk plus 1 times this minus that. Yeah? So this is the change in v's, and the change in v's is the same as the integral of the acceleration. You see, this is kind of tricky. So now we have this. By the way, I encourage you guys to revisit this proof at home to make sure, A, that I'm honest, and B, that you actually understand what's going on. It's easy to be agreeable and then get to the last step and figure out that you didn't actually see what was going on. Okay, and meanwhile, we also have to subtract off what we had before. Which is TA. Yeah? Well, now look. See, I was very clever. I kind of knew what I wanted ahead of time. And now we have an integral over the same bounds of two different things that involve a, so we can stick them together. And in the end, we end up with yk plus hvk plus the integral from tk to tk plus 1. And now we're going to have a of t times what? tk plus 1 minus t dt, and that is exactly, I hope, yes, the formula that is up on the screen. All right, amen. So, all this is, in fact, if you want to prove Taylor's theorem, then what you'll do is you will inductively write down a proof like this, and now you're going to change that a into a third derivative, and then a third derivative, and a fourth derivative, and each time you do that, you get another power of this number here. Right? So one proof of Taylor's theorem says that this integral goes to 0 as you take higher and higher order approximations. Yeah. It's actually a pretty direct proof. I haven't seen that one before. Okay. Now, in case I didn't write down enough complicated formulas for you, we're going to need one more, and then I promise you the smoke is going to clear over that. Okay. And that is this third one down here. Anybody have a good intuition where the heck this one comes from? No, because I didn't. Okay. So here's what we're going to do, is we're going to say, okay, let's say that I take some tau that's somewhere between A and B, right? And then I can write a Taylor series about tau for my function, and use that to approximate both A at time tk and A at time tk plus 1. Yeah? So let's say that we do that. Well, then we're going to have that A at time k is equal to, right, the usual formula, A at, gosh darn it, A at tau, right, plus A prime of tau, tk minus tau, right, this is a negative number by the way, plus order h squared. If you look at the mechanical engineering book that I cited in the notes, they work out a bunch of terms here, but I don't think they're really easy. Okay. Similarly here, we can say ak plus 1. Well, he's just a at time tk plus 1, so it's going to be the same formula, right? A of tau plus a prime of, that should be tau again, tau tk plus 1 minus tau plus order h. Okay. So what I'm going to do is I'm going to take this guy, and I'm going to multiply the whole thing by 1 minus gamma for any constant gamma. I'm going to take the whole second guy, and I'm going to multiply him by gamma. Right? Now, why would I do that? Well, notice that we're basically taking a weighted average of these two guys. So this term stays the same. Right? So in particular, I'm going to move the a of tau to the left, and I'm going to move these guys to the right. I know this is a little tricky, but there's a reason that we're going to do this in a minute. Okay, so in particular, when I do that, then I will get a really funky expression for a of tau, which is that he is equal to 1 minus gamma ak, right? Because that comes from this guy. But there's a... Did I do this wrong? No. Okay, yeah. Right, so we're going to subtract off these two terms and put them on the left, yeah? So in the end, I'll get 1 minus gamma times this, plus gamma times ak plus 1, yeah? And now we have to look at these two terms, and what do we get? Well, we're going to get, notice that they both have an a prime of tau again, of tau. And now we have this funny combination of gamma minus 1 times tk minus tau minus gamma tk plus 1 minus tau. All that plus order h squared. Right? So at least the order h squared term is clear here. And this term is clear because we're just taking the weighted average of these two rows. Yeah? And this guy, if you look, I got a gamma minus 1 instead of a 1 minus gamma because I moved everything to the other side. Cool? I know there's a little bit of arithmetic here. But it turns out this is a very large class of integrators, and that's why we have to be a little careful. Now, we know we have an expression that tk plus 1 is tk plus h. Right? So if we plug that in here and simplify a little bit, hopefully you will indulge me and allow me to tell you the end trick of doing algebra in this term, because it's not humongously exciting, is that you end up with the same two terms initially. And you should check this at home, by the way. I can't force you to do it on your homework anymore, but you should do it. Oops, sorry, no tau. And then this funny a prime of tau, right? He's just sitting, this tau is just sitting somewhere between a and b, but then in the end you get this nice formula, tau minus h gamma minus tk. Turns out it's what this whole term simplifies. Order h squared. Okay. And hopefully, yes, that is exactly the formula I have on the board. So these are the 3 observations about life that we made. Right? The first one is abundantly clear. The second one is just Taylor's theorem, where we explicitly wrote out the remainder. And the third one is this funny thing where we took a Taylor series centered at tau and we used it to predict AK using different weightings of the two possibilities of it. Yeah. All right. So that's all our hard work. We got lots of integrals in math. I should like Instagram this or something. Okay. So now we'd like to derive a class of integrators from these. And in fact, I didn't give myself very much help on the slide, so we're going to keep these formulas up here and do a little bit more work, which is this. Is it okay if I erase the left board, by the way? Going once, going twice? Cool. I know it's not 100% clear on the video. You know, on YouTube, I'm posting these things, actually just because I'm too lazy not to. They're all posted in HD, and if you turn on the HD option, you can actually read the board. I checked this. But it also makes my laptop overheat, so you can only watch 20 seconds at a time. Okay, right. So to time step our velocity forward, we're going to apply our first formula here, right, which is that v, wait, how am I doing on time? Okay, k plus 1 is equal to vk plus the integral from tk to tk plus 1 of a of t. dt, right? Well, here's the kind of funny thing that happens. We now have an expression all the way over here for a of t. I use tau, but whatever. Right? And if I integrate this guy, right, what's going to happen? Well, I'll get the integral of this expression, at least these first two guys with respect to tau, that is, there is no dependence on tau. Right? So what's going to happen is you'll just get an h next to these two ones. Right? And then when you integrate this, you're just going to get plus big O of something. And in particular, plus order h squared. Right? Why do you see that? Well, look, this thing looks like, right, so you already have an order h here, right? This is tau minus tk. Remember that tau is somewhere between tk and tk plus 1, right? So this number is also order h. So this whole coefficient here is order h. You're integrating this expression from tk to tk plus 1, so in effect you're multiplying this whole thing by another order h. So this whole term when you integrate is order h squared. Yeah? In other words, this expression as written here just looks like something with an h in it. That much hopefully you agree. And when I integrate an order h thing, I get an order h squared thing. You can check this at home, but we're a long time. Okay? So if we do that, well, that gives us our first formula in the Newmark. Well, I guess I wrote it in the second formula. But you can see here that all I did was I integrated that guy and just removed the quadratic terms. Yeah? And what is our first formula here? Well, for some reason, for historical reasons, so remember we have a second formula for integrating to get yk plus 1. And remember, basically the idea of the Newmark class is that we only want to have to do integrals involving a. Right? We're going to do a little bit of work on this second line here to make our time step for y look like an integral involving a instead of b. Right? That's sort of from a high level what's going on. So, right, so if we plug in this form for at here, right, we can integrate that out, and I don't think I'm going to bother doing this on the board, it's in the course notes. Then you still get a quadratic term, but the choice of gamma that you use in this yk plus 1 does not have to be the same gamma you use to approximate v. Right? Because no matter what gamma you choose, this is still an order h squared approximation. Right? So what Newmark says is we're going to use one gamma for time stepping the velocities, so that's what we just did. Then we're going to use another gamma for time stepping the positions y. Right? So to distinguish between these two things, he uses beta for the y step, and he uses gamma for the velocity step. Yeah? And for some reason he puts in a factor of 2, which you can do. Gamma is just a constant, so if you want to multiply by 2, you can. And that gives you the famous, I present to you, the famous Newmark class of ODE second order integrators. Yeah? And now, hopefully, even though we skipped a couple steps toward the end, you can see how it's actually not so hard to derive. Yeah, just lots of algebra and calculus. Okay. So this is a class of integrators, and it is parameterized by two numbers, beta and gamma. Right? So for each beta and each gamma, you get a different time-stepping scheme. Right? And so basically what you can do, to your heart's content, is choose different betas and gammas and see what kind of physical output you get for your simulation. In particular, there are a couple classes, choices of beta and gamma that people use in practice, and we'll mention those briefly. By the way, you should notice that depending on beta and gamma, your method could be implicit or explicit. Right? For example, if beta is equal to 0 and gamma is equal to 0, then this is an explicit method because I have zeroed out all the ak plus 1s on the right-hand side. Yeah? Okay, so there are lots of different methods. For example, if we do exactly what I just said, then you get this integrator here, which is really nice. This is called the constant acceleration integral, and that's because if a were just a constant in time, then this would be exactly the solution you would get. Yeah? So this is exactly correct for constant accelerations, very incorrect for lots of other accelerations. People use this in computational physics sometimes because somehow